What do spinning wheels and ship stability have in common? Hello everybody, I am Nick the Naval Architect. How does a Seakeeper work? If you look at the marketing videos, they show this strange ball that pitches back and forth inside the ship. And somehow this magic stops the roll motions for that boat. Well, how, you might ask? What black sorcery is going on here? Now, the average person will give you a vague explanation. They'll mention that the ball contains a spinning flywheel, and then they will desperately hope that you don't have any follow-up questions. Truthfully, the Seakeeper does take a little effort to fully explain. It isn't intuitive. Gyro stabilization invokes some pretty weird physics. So, let's explain gyro stabilization. How is the Seakeeper so effective at roll mitigation? I would be remiss if I did not mention that Seakeeper is not the only brand of gyro stabilizer that's on the market. They're just the brand that will most likely show up at the top of your internet searches. So I may use the term Seakeeper interchangeably with gyro stabilizer. This isn't an endorsement for one brand or another. I'm just here to talk about the technology of gyro stabilizers in general. The first thing we need to talk about is angular momentum. Ships, they don't stop on a dime. At some intuitive level, we all understand momentum. Push a heavy boulder forward, and it takes a lot of force to stop that boulder. If you want to sound fancy, we call this the conservation of momentum. Heavy things want to keep moving. What's a little less intuitive, though, is that the same concept applies to spinning motion. A boulder that's traveling in a line has linear momentum, but a spinning boulder has angular momentum. Spin the boulder, and it takes a lot of torque to stop that boulder. Technically, the mathematics are slightly different with angular momentum, but we'll keep things simple for now. Now, where it gets really interesting is when we consider three different dimensions. Remember that we live in a three-dimensional world with three different directions: X, Y, and Z. And in this world, we get three different sets of angular momentum, one for each of the three directions. Here's the interesting question. How do those three sets interact with each other? Hint, weird things can happen. One of those weird things is a gyro. Gyros take the basics of angular momentum and start exploiting those principles for some really fun effects. So the basic idea behind a gyro is take a small disk and spin it really, really, really fast so we can contain a lot of angular momentum packed into a very small object. But remember, the really neat stuff happens when we start thinking about three dimensions. Think about that spinning ice skater. She's just spinning vertically, rotating about the z-axis only. But what if we could tilt while we were spinning? Well, what happens then? This is the really fun part behind the gyros. If you take the spinning gyro and force it to tilt the axis of rotation, the gyro is not actually going to rotate in the direction that you're pushing. Instead, it's going to rotate about the third direction. So you've got the direction that the gyro is spinning in, the direction that you're pushing, and the gyro will actually rotate the third way. We call this gyroscopic precession. So if you take a gyro that is spinning around its z-axis, apply a torque, tilting that gyro around the y-axis, and then the gyro behaves weird. Instead of following the direction that you pushed, it takes this new motion and redirects it. So a torque to rotate about the y-axis instead actually creates motion around the x-axis. So why does any of this matter for seakeeping and roll stabilization? Well, we can use gyros to stabilize the ship motions. If you take a gyro that is spinning vertically and mount it on the ship so that now the ship and the gyro are rolling as one unit, this is what happens when waves are trying to roll your ship from side to side. But the gyro doesn't like this at all. No, no, no. gyroscopic precession kicks in, which is now going to reduce the roll motion. Now, to understand how this works, we need to break this down step by step. And it's best to think of the ship and the gyro as two separate items. These two are going to trade forces between each other following their own rules. So first thing that happens is the ship rolls about its x-axis. That's the roll direction. That roll motion is now also applied to the gyro. Rolling the gyro on the x-axis, though, that creates gyroscopic precession. And the gyro stabilizer does allow this to happen. So even though the gyro gets a torque to roll about the x-axis, instead, it's going to try and react by pitching around the y-axis. The math tells us that if we have this y-axis rotation, the gyro is going to create a reactionary torque and kick back around the x-axis. Going back to our ship now, that x-axis torque from the gyro gets applied to our ship, and it fights the rolling motion. So instead of our ship just rocking freely, the gyro kicks in and provides a reaction to stop the roll motion. Now there are a few more subtle things that are happening here. If our gyro were just free to pivot about its y-axis, to do its precession thing, eventually it's going to rotate a full 90 degrees until its spin axis is in line with the x-axis, with our roll motion. Now at this point, the gyro would not notice the ship's roll from a physics perspective. We wouldn't get any more gyroscopic precession, and the whole stabilizer would stop being effective. So we need something to counteract that precession and restore the gyro to a vertical orientation. Seakeeper decides to counteract that pitch through a hydraulic brake. These are two large hydraulic cylinders that are sitting on the side of the gyro. Going back to our model of the ship and the gyro, let's examine what happens when that hydraulic brake does its thing. So first, the gyroscopic precession creates a torque. It's trying to rotate the gyro about the y-axis. Now before we just said that it would do that freely, but now let's consider what happens with that hydraulic brake. So the hydraulic brake is going to allow some precession. We need that. We need a little bit of precession to counteract the roll motion. But after a little bit of precession, the brake kicks in. That brake then creates a counter torque. It's stopping the precession. But now you have to ask, okay, where are the forces from that brake going? The torque from that brake, it's then transferring back into the ship as a reaction force. And this is going to try and rotate the ship in pitch motion. So you can kind of think of what's happening here is the gyro is taking some of that torque from roll motion, and then it's doing its precession thing to convert some of that momentum into pitch motion for the ship again. Why do I keep repeating this? What's so important here? Well, it's important because most monohull ships are long and skinny. Their shape means that they resist pitch motions far better than roll motions. So by converting that roll into pitch, we're using the strength of the pitch motion of our ship's hull to reduce our roll motions. Pretty neat. Now, one of the unique innovations for Seakeeper is specifically how those hydraulic brakes activate and control the gyroscopic precession. If you look at the animations from Seakeeper, you might think the hydraulics are actually the ones moving the gyro. But no. Those cylinders are just a brake. When you release a Seakeeper gyro to start rocking, those cylinders actually release from being clamped down. The roll motion of the boat itself and the physics of gyroscopic precession are what caused that gyro to start pitching back and forth. And I have to admit, this really confused me at first, because when the gyro stays locked down, you can see that there's no roll mitigation. The ship behaves like it doesn't have a gyro, even though the disc inside the gyro is already spinning, but it's locked vertically. And to really understand this, you have to run through the math. It turns out that gyro stabilization depends on both the speed of the gyro and the speed of gyroscopic precession. If you stop either one of these, all of the forces go to zero. But if you then ease off that hydraulic brake, the physics start to kick in. This hydraulic brake is really the key to making a Seakeeper so effective. So when we dig into the physics, the torque that we get from a gyro stabilizer, that torque depends on the speed of roll of your ship, the angular velocity. Well, that's not a constant thing. In mild seas, you're going to get very slow roll speeds, very low angular velocity. And in that scenario, for effective stabilization, we need a big gyro with a very fast rotation speed. But the situation reverses if you go to large seas. Then you've got these big waves, and you actually get large velocities, really jerky motions. At that point, you actually need to fight the physics, to temper your stabilization by getting a smaller gyro, a slower rotation speed. So when we have small waves, we want a big gyro. And when we have big waves, we want a small gyro. Except you can't have it both ways. The gyro is a fixed size, and it really does take a lot of energy to alter the rotation speed of that gyro. So you're not going to be changing these things on a second's notice, which is about how quickly you have to react on the water. So how do you create an adaptable gyro without changing all the physical parameters? Well, if you can't change the parameters, change the timing. When you have that hydraulic brake, Seakeeper can control it with a computer and rapidly switch the state of gyro stabilization. You can constantly flip between on and off without altering the gyro itself. And that's because the brake controls precession of the gyro. If you don't have precession, you don't have roll mitigation. And given the fact that it's a hydraulic brake, that means you can also do partial roll mitigation. You can allow a slower precession, not just on and off. This adaptability means that you can oversize your gyro to handle light wave conditions, but then in heavy conditions, the hydraulic brake can control that effect, only allowing partial precession. So by controlling that hydraulic brake, you're taking what was a single gyro and making it adaptable to a whole range of wave conditions. That's pretty clever. The second major innovation for Seakeeper lies in the computer that is controlling that hydraulic brake. See, the computer is constantly sensing the ship's roll, not just the roll angle, but also the angular velocity and the angular acceleration. With all of that monitoring, we get a bit of fortune telling. On a small time scale, ocean waves are kind of predictable. If you're only trying to look forward 5 to 10 minutes, well, normally you're going to see the same ocean waves, the same period, the same amplitude. Sure, we still get some random variation on top of that, but there's a dominant pattern that you can see. And the computer can detect that pattern. So once it knows the pattern, it can predict the future. The computer can sense where you are right now and then predict where your boat is going to be 1 second into the future, what kind of torque it's going to encounter in terms of roll motion. And that allows the computer to adjust the hydraulic brake and start the gyro responding before the wave even hits you. This is how a Seakeeper is so effective with roll mitigation. There's very little delay between a wave hitting you and the response from the gyro to counteract that torque, because the computer already knew it was coming and responded to it before it even got to you. Now for a little practical advice. Gyro stabilizers should not become a universal solution. They do have their limits and their problems. For example, the underlying physics depend on the ship having much more stiffness in the pitch motion than in the roll motion. Now for monohulls, this makes sense. But if we start talking about multi-hulls, catamarans and trimarans, this is not true any longer. Gyro stabilization is much less effective when we're talking about multi-hulled vessels. The physics also suffer from a size limit. As ships get larger, we need more and more torque to counteract those roll motions. That means bigger and bigger gyros. Well, as the size of that gyro increases, practical problems start to creep in. It becomes very difficult structurally to handle the torque that's coming off of a supersized gyro. So that's why we generally don't use gyro stabilizers if we're talking larger ships. Things over, say, 30 meters, gyro stabilizers are not your only option. There are alternative technologies available when we're trying to do roll and motion control. Other options like stabilizer fins, bilge keels, hydrofoils, interceptors, trim tabs, azipods, rotors, U-tanks. The list goes on and on and on. The best solution for your ship is going to depend on a lot of factors like the size of the ship, your speed, the mission, and your budget for motion control. This is where a naval architect steps in to figure out the best combination. For my own personal preference, rather than immediately going to a Seakeeper, I prefer to use gyro stabilizers as just one component in a whole system of motion control. And I will normally start by considering the cheaper alternatives first, like bilge keels, and then supplement them with more advanced solutions like a Seakeeper. Hey, you're still here! Then let's wrap this up. So we've talked about gyroscopes in general, and the major advantage being that they can pack a lot of angular momentum into a small package. You combine that with gyroscopic precession, which is a neat little bit of physics, and you get a gyro stabilizer that we can use on a ship. Basically what it's doing is taking some of that torque from roll motion and redirecting it into pitch motion. And credit to Seakeeper, they took the classic concept of gyro stabilization and added in all of the control systems to create a truly adaptable and effective device. But the core principles behind it, they still depend on gyroscopic precession. It's still the same physics that we've known about for decades. And it's that weird bit of physics that couples roll motion with pitch motion on a ship. If you apply this on a monohull, the gyro stabilizer is a major advantage. There's no magic involved. It's a machine just like any other, with limits and best case applications. But even I have to admit, this is a pretty impressive machine. Thanks very much. I am Nick, the Naval Architect. How on earth do they do it? Have you ever wondered how the large commercial ships do all these amazing things? DMS brings that same engineering to smaller operators. Take the chance to create a high-performance ship, stand out from your competitors. So check out the website, and together, let's build something awesome.